Thank you, Joey, for the introduction. So I'm Jordan. I'm a PhD student at the University of Wisconsin-Madison in the Department of Chemical Engineering. For this talk, I want to share some of the developments we made with our Julia package, Plasmo.jl. And that actually is an acronym. It stands for platform. The PLA is platform for scalable modeling and optimization. So you just kind of have to know what the acronym is. It doesn't make sense from the text. Call it Plasmo because originally we wanted to have a good platform to go after modeling really big, complex optimization problems. But the more we did different applications, the more we realized that type of complex system problems we're trying to model were really often cyber-physical systems. So Plasmo is it's a good package to kind of model and approach this class of problem. And these systems are interesting and challenging for a couple of reasons. They have both physical and computing aspects to them. Specifically, those physical aspects usually include you've got lots of component models that are physics-based, and a lot of the complexity comes from the physical topology. For instance, of a network, you have lots of physical connections, such as conservation constraints or boundary conditions. Those physical systems are often driven by computing systems, and in our field, it's usually a control system. And those computing systems can be very complex to simulate, especially when you want to consider things like latency and delays, and especially asynchronicity. Trying to understand how asynchronous systems are actually behaving, that's a hard thing to do. But as we were doing the kind of control system design, we realized that these computing aspects also really correlate with this idea of just a general computing system. So for instance, you might want to simulate how an algorithm, an asynchronous algorithm, might actually work on a high-performance computer. So you might not have access to an HPC system, but you might want to have some idea of how would my algorithm actually scale if I was going to write a parallel implementation. So Plasmo tries to approach these two problems. We want to solve large-scale optimization problems, and we want to try to simulate a real-time system. So the graph-based modeling package. And so first I want to go into how we model those large physical optimization problems. For that, we came up with, I think, a simple idea. It's an algebraic graph. In the code, it's actually called a model graph. And it's straightforward. What you do is you associate component models with nodes, and then you're going to link them together by means of algebraic constraints. These are going to be linear equalities or inequalities. So doing this kind of structure, it's going to give you this formulation. You're going to have the sum of the objective functions of all the nodes. Each node is going to have its own constraint set, and then you've got these linking information for the system. And so if you blow this up, you blow this connectivity matrix up, you can see how each edge in the system, how its linking constraints relate different variables to different nodes. And so the idea is you can use this linking information, one, to really understand the topology of your problem, but two, we might be able to use this decomposition, and I'll show how to do that. Point, this is all just JuMP models that are associated with nodes. So if you understand how to use JuMP, then you pretty much already know how to use this aspect of Plasmo. You're just creating JuMP models, and you can link them together. And here's an example of how you would do that. So you load the package. Right now, we're still using JuMP 0.18, so that's on the to-do list just to update that. So you'll see some of the old style syntax here. But the idea is that any of the solvers that are available through JuMP can be made available through Plasmo very easily. What you're going to do is you're going to create a model graph. You're going to have a solver for that. You're going to add nodes to it. You're going to have your JuMP models that, in this case, I parameterize and created with these functions. But you're going to set models for those nodes. And that's a key distinction. We keep the topology and the model separate. And that's useful. That's really useful for cases where you might have some initialization strategy. You're solving a big system graph. Then you want to swap out certain parts of the model, and you can just swap out the models on the nodes and then throw that solution and do some sort of warm starting. It makes it really easy to do that kind of approach. And then the real workhorse is just creating this link constraint here. And so this works the same as a JuMP constraint macro. In fact, it actually more or less wraps the constraint macro, but what it's doing on top of that, it's defining that hypergraph topology, how these nodes are connected by this collection of edges. And then you can solve it. And in this case, we're solving with IPOP. We're not really using the structure, but we can still put the solution back in that structure. So we're solving it in a serial optimization solver, but we're getting a structured solution. And that's useful for some of our use cases. What you can also do is you can use this to model big hierarchical systems. And so in some cases, you might want to have individual sets of nodes for your model graph. You might want to do two systems independently, and then just have an easy way to link them together after the fact. And so in this case, you might have model graph 1, model graph 2. You just create a bigger model graph and say, these two systems are connected at this higher level. So you get this formulation here, and it's the same, it's kind of a bottom-up approach where every single node is in the highest level graph. Our objective in this case is still the sum of the objectives of the nodes, subject to the local constraints, but now the connectivity information is localized to the graph. So each subgraph and graph on top of that has its own edge information. So that's how we manage the topology. So this is really useful for some of our use cases. We do some modeling and infrastructure systems. So in this case, if we wanted to do like a coupled gas power infrastructure, what we did is we created the power infrastructure model, created the gas infrastructure model, using the syntax I showed before. And then what we can do is we can actually link the systems together after the fact, so we can maintain these models separately and then decide how we want to link them. And that's an example of how that would work. So again, using the same packages, some include functions here. So we're assuming we've parameterized. We have our functions that are creating our graphs for these Illinois gas and grid systems. And using this Illinois system because it's something we have data for. So it's a really nice, big, juicy problem we can use to test this modeling platform. Then you would create this combined system. So say I have a new model graph. We're still going to use IPOP in this case, and then we're going to add the subgraph to the combined system. So this is going to add. This is going to do that hierarchical topology. And in this case, we would just say, okay, I'm just going to query for a couple nodes from each graph, and then I'm going to link them together in the higher level graph, and then I can solve that. So this is a really nice way to manage the complexity when you're trying to build really large hierarchical-based models. But in this case, I'm still using IPOP, so I'm not really taking advantage of the decomposition structure yet. And it's a graph-based modeling platform, so we want to be able to do that. So I have to give some acknowledgments to my colleague, Bralo Granad. So he saw this modeling platform, and he was able to pick that up and start running away with it and developing his own decomposition algorithms using this model graph object. So it's really too bad he couldn't be here today because he actually spent probably 15 years in Santiago before he came to the US. But originally he wrote his own little package, and then we migrated all the algorithms he wrote directly into Plasmo. So this idea is very simple. Again, you're creating these models, you're going to set them to the nodes. But the idea is that we have this collection of Plasmo solvers. So for example, he wrote a Lagrange solver that we hooked directly into the Plasmo graph model structure. So you can create this Lagrange solver, parameterize it at the different methods you want to have in the solver. So in this case, we're just going to use the subgradient method to do the dual update. We've got the link constraints. In this case, we're going to solve the graph in this way. So this is really nice. We can express these graph structures to a decomposition algorithm in a very generic way, but we also might have very big graphs. So in this case, every single node is a subproblem, but in really large graphs, you might want to think of a better partitioning scheme for a very complex structure. So that's when we started developing more of the graph decomposition capabilities. So you can imagine, for instance, you've got your model graph following this formulation. And the idea is you can take something like this and get partitions of the optimization problem itself based on that linking information. So what we can do with Plasmo is partition a problem like this, and we can express that to solvers that would understand that. That would mean different things to different solvers. So for example, if your solver is doing some linear algebra decomposition, for example, pips and LP is going to solve a linear system that has this ordered block diagonal form, you can express those partitions directly to that, and you have that pip solver available to you. In case of Lagrangian decomposition, these partitions would really just correlate to the subproblems themselves, and then you would go through, solve all your subproblems, do your dual update. And there's other decomposition algorithms too, but that's something we're constantly working on, is really getting more of them into the package. So here's an example of how to do that. So we really wanted to make modeling and applying a decomposition algorithm as straightforward as possible. So in this case, we would say we're going to use Plasmo. We have the solver interface, which has the pip solver, or Plasmo's interface to the pip solver. So we'd create the Illinois gas system here again, and in this case, we can use Metis, which is a very traditional graph partitioning package. And then we can actually use Metis to partition the model graph and say I want to get 8 partitions. We'll say Metis, give me a k-way partition of 8 partitions, and then using this little pip solver object, we'll pass those partitions into pips and say, okay, pips, you have these 8 partitions to work with, and then the algorithm can do its parallel implementation. And so this was really nice. So here's the actual partition of that Illinois gas network problem. So this is a gas dispatch, optimal gas dispatch problem. So we're able to partition this and give that to pips, and pips can solve that in roughly 40 minutes. And this is about a 1 million variable nonlinear program. So for our purposes, that was very encouraging for this type of system. It actually it suggests we might be able to go after kind of these infrastructure systems that could be much bigger regional, national type scale systems using just general decomposition strategies. And then we're also interested in doing more community detection-based approaches. And so this is a little different than the partitioning. In graph community detection, in this case, we're more interested in finding communities of nodes in the graph that are more connected to each other than nodes in the rest of the graph. And so in this case, we're finding ways to get communities in these optimization problems and then be able to express those communities as partitions to the solver in the same way. So in this case, we found out that the solenoid system has 5 communities. So it's not, we don't have as much control yet using a community detection algorithm like this to say how many partitions I want. But the idea of the community detection is that maybe these are very high quality partitions. And the point is this is something we can actually mess around with. And so these algorithms are something we're actually currently trying to add to the community detection package, which surprisingly, this is an inactive package. So this code won't work until they actually merge the pull request I did a few weeks ago. So I talked about how we use these algebraic graphs to model and solve big system type optimization problems. So now I want to show how we can, for instance, maybe develop a decomposition algorithm and simulate how that might actually work on a real-time system. And so the key difference here is in this idea of the computing graphs to do that is that opposed to associating optimization models with nodes, we're associating these dynamic tasks. And so you can think of task as a function. It could be solve a JuMP model. And that these nodes are going to communicate information to other nodes in the form of data. And so the idea here is we want to be able to simulate the behavior of an algorithm on different computing architectures. And so the real challenge with doing that kind of simulation is ultimately, you've got the delays and latency, but the asynchronicity, having lots of different actors moving at the same time, they're communicating information, that's a really hard thing to deal with and really manage. And so we came up with these key elements of this computing graph to try to manage that. And this is just a more blown up detailed version of a computing graph. You've got these different nodes. They're going to have their computing tasks that they can run. And these nodes are going to have defined attributes. So in this case, each of these nodes has these attributes, and these attributes can be communicated to each other. So really the key elements that really define all of this are the nodes with their tasks and their attributes. These tasks are going to have a real compute time, and that could be the actual compute time your laptop took to evaluate a function. The edges are going to do communication, and that's going to take a real amount of time. And then everything's happening at the same time. So we needed a way to manage the asynchrony of the system. And so we have this kind of global clock, which does the scheduling management. In this case, just to manage the simulation. We want to make sure we're not violating any causality issues with an asynchronous simulation. And then I didn't really go into when nodes run their tasks and when they decide to communicate information. And for that, we came up with this, I think, very clean, kind of cohesive state space description that describes when nodes do things and when edges do things. And a lot of that kind of comes from our background in control theory, and we really like being able to express systems in this state space form. So the idea here is that these nodes or edges can be in different states, and they're going to make these transitions based on signals that they receive. And with every transition, there's going to be a corresponding transition in the attributes of the node or the edge. So every time the node is changing some sort of state, it's making some transition in its attributes. And we can use this to help manage the timing and manage the behavior of the simulation. And so we put all this together, and ultimately, you would get something that looks like this. So we could have different nodes. They're all running their tasks at the same time. The nodes take compute time. The tasks have actual communication delay. You can get a lot of different behaviors, which is why the state space description is really nice. It lets us handle a lot of the different cases that can come up in this kind of simulation in a very general way. So for instance, it looks like here, this task on node 2 seems to execute when he receives his information from node 1, receives this attribute. But you can also get cases where looks like node 1's executing his task. He receives information from the other node, but it looks like in this case, he keeps continuing his task and he more or less ignored it. So you can have different things that pop up depending on what state these nodes are in. So for instance, it might have been that he decided to interrupt what he was doing and do something else. It might have said, maybe I need to do this task, but I'm going to wait till I'm done. So there's a lot of different behaviors, but that state space description was a really cohesive way to really capture all of that. And then I should mention that right now, all this clock is this is all managed from a discrete event queue. So if you're really familiar with discrete event systems and discrete event simulation, this would be somewhat familiar to you. And so I think it's easiest to show this with just a simple example. And I guess fortunately, people have been explaining Bender's decomposition today, so maybe this will be a little easier to understand. I like Benders decomposition because it is, I think it is a very simple concept to get at this level. The idea here is if we wanted to simulate Benders decomposition on a parallel system using this computing graph for a very simple case with 3 nodes, we would say there's going to be one node that's going to have a task to run that Benders master problem. I'll have another task that says, what do you do when you receive a solution from a subproblem? And then we'll say these nodes are going to, their jobs are going to be to solve these subproblems. What they're going to do is they're going to communicate information. The master will communicate a master solution, and then he'll also communicate scenario data for these subproblems to solve. And these subproblems will return solutions back to the master. So if we take if you look at the trace, this is a trace plot. If we take a trace of just 2 nodes, this would be really simple. The master's computing his task, sending his data, and then this sub node starts doing its work, sending it back. The master's receiving data. It looks like when he receives them all, he starts again. So the idea with doing this kind of simulation framework is that we want to make it easy to actually evaluate, in this case, different algorithm variants on a parallel system. So it would be possible to use this computing graph to try to simulate either a synchronous or asynchronous variant of the algorithm, and I'll show what that looks like. So in terms of the code, so this would be the Plasmo implementation of how you would set up a computing graph to do this kind of simulation. I should put an asterisk here. So I haven't finished writing the macros yet. So right now I had to do all this just using the normal function API. But this is what the macros, these are what they're going to look like. So you'd create the computing graph. You would add your node. It's very familiar. The idea of adding attributes just means these are attributes that have special meaning. These are the attributes that can be communicated and will do things like trigger signals to nodes and edges. We can add tasks to nodes. So in this case, we can say, this master node, give it the task, run the master. You can give it arguments. Give it itself if you want to access information to that node. So in this case, I'm not showing it, but this would just be a run master function. So that function would contain, what do I do when I solve the master problem? So that function might be solve a JuMP model that contains the master problem. You can give it compute time. So the default is going to be the wall time, so however long your laptop took to actually evaluate that function. And then we say that the task is going to be triggered by it updated an attribute. So inside of that function, you might say update this attribute, and it's going to catch that and say, okay, I need to trigger this task, so it's ready to go. It's going to be very similar for the receive solution. We'll assume that it takes no time to receive a solution, but you could add something. And then we'll say this is triggered every time it receives this attribute solution. We can initialize the graph, so we use signals to kind of manage everything. And then we would add the subnodes and the connections. So we tried to make this as intuitive as possible. Create the subnodes, has its attributes. Subnodes have their tasks, such as solve a subproblem. This is going to be triggered by receiving their scenario information. And then we're going to make the connections. And then just kind of similar to this triggered by, we have kind of an action mapping that tells when do these nodes send their data. So in this case, these nodes are going to send their data when this master is going to send its data when it has an update to that attribute, that master attribute. So that in that function, in that run master task, you'd say you'd run it, you'd update the master solution, and that would signal to this node that it updated, and it would notice in that information. And then you would go ahead and execute the graph. And you can say, you can also say how long you actually want to do that. And so this would be the result of doing that for the synchronous case. So what I set up there was that's very close to what the synchronous implementation looks like. So this is a simulation of synchronous Benders decomposition just on my laptop. So I parameterized it around 4 CPUs. I say CPU 4, you're going to run the master. It sends this information to the subproblems, and you can see how long each of those took. They send their information back, and you can see it go through the iterations, and it terminates over here. So what we got from the synchronous simulation is something we might expect, is that we get a poor parallel efficiency. Because what we're seeing here is that the master problem is waiting for all of the subproblems to complete before it re-executes. And so that's what all of these empty spaces here are in this trace. So this is a plot that you can spit out of Plasmo. So if you create a computing graph and you run it, you can just generate what did the trace, what happened with all the nodes and all the tasks. Yeah, we're good. And then so this is the last slide. So this is just if we just change it a little bit, just change the computing graph and change those tasks just a little bit, we can get the asynchronous variant of the algorithm and simulate that very easily. So in this case, it looks like it actually took a little bit longer to complete the algorithm because I had to run more iterations. But that's because what the asynchronous variant is doing is instead the master is saying, I'm going to wait for a certain fraction of these subproblems to complete. I'm going to run the master again. And then you see that it takes a little bit longer, but you get a better parallel efficiency. And a lot of these nodes are, they're not spending a lot of time not doing anything. So while in this case, it took a little bit longer in the simulation, you might expect that this might scale better on a larger system. And that's something that you could test using this kind of paradigm. So that's really it where we are with Plasmo. Currently, really on the to-do list is we do need to do the update on the model graph to handle JuMP 0.19. We're really trying to clean up the interface to really express the decomposition algorithms, and we're trying to add more decomposition algorithms and make it very easy to, really just have a general way to say, here's my system, here's my problem. Can you find a decomposition that is very suitable for this problem, and just have that happen automatically? And then on the computing graph side, we do need to clean it up. We need to finish the macros. We need to write the documentation for how to use these computing graphs, because this was a very complicated concept when you came up with it, and kind of having that whole state space description really helped it out. And what I showed you was really just the surface of what a novice user might use, but there is this underlying kind of action transition behavior that you can expose to the user, so you can have a lot more fine-grained control over what's really happening in the simulation. So I think that's where we're at, and if we have time, we'll take a few questions.
How tight is it to the other JuMP solving part of the problems? Because you have part of the Plasmo which is solving optimization problem, and the other part which is orchestrating all that.
So that's a good question. So it's almost worth considering having them as two separate packages, because what they do is really so different. They're all in this monolithic Plasmo. I mean, that really just for a branding is, yeah, it does all these things. It simulates and helps you solve problems in cyber-physical systems. But really where they're connected, I think you could use these computing graphs to actually write algorithms if we set it up in the right way. So I think it would be possible to, instead of saying I'm just going to do the simulation, I think we could have another executor of the computing graph that says, okay, you set up the algorithm kind of with these nodes which have these functions. Maybe I can execute this algorithm asynchronously in a very generic way. Maybe it could be a good algorithm development platform.
So could you have like multiple layers of vendors? So if you have a very hierarchical system where you have like one level of master and some problems, and then above that you have another master, is that like automatic?
So like a nested vendors.
Yeah.
Yeah. So that's it's also a good question. So that's a limitation that I'm really thinking about. So we can do a reformulation at least for just a bi-level, like a master sub. We're thinking of a way to do a graph transformation that would be able to find that kind of structure. So the way it works is whenever it does the decompositions, we take the hypergraph and we're doing a graph transformation that we're doing a projection to a different space where it can kind of find what these partitions are. So I think we would have to find a more suitable graph transformation that would detect that kind of hierarchical structure. But for right now, it just does a 1 and 2 stage, and it does Lagrangian and type decomposition very easily. That's much more natural to how you model.